Hey everyone, welcome back to Physics Vault, where we dive deep into the universe's biggest mysteries without dumbing them down. Today we're talking about one of the most legendary discoveries in all of science, the Higgs Boson, the particle everyone loves to call the God particle. We're going to unpack exactly why this tiny thing is responsible for giving mass to every single particle in the universe, how it works at the deepest level, and why its discovery in 2012 was an absolute game changer that completed one of the biggest puzzles in physics. Buckle up, this one's going to blow your mind. Let's start with the obvious question. Why do we even call it the God particle? The nickname didn't come from physicists being dramatic. It actually came from a 1993 book by Nobel laureate Leon Lederman. His original title was supposed to be The Goddamn Particle because the thing was so hard to find. The publisher changed it to The God Particle for marketing, and the name stuck forever. Peter Higgs himself hated the nickname. He thought it was disrespectful to religion, but the name caught fire because this particle really does sit at the heart of why anything in the universe has substance at all. So what actually is the Higgs boson? To understand it, we first have to understand the Higgs field. Imagine the entire universe. Every single cubic centimeter of space is filled with an invisible field. Not like a magnetic field or gravity field that you can turn on and off. This field is always there. It has a constant value even in completely empty space. That constant value is called the vacuum expectation value. When particles move through this field, they interact with it, and that interaction slows them down. Exactly the way running through water slows you down. That drag is what we experience as mass. The stronger the particle's coupling to the Higgs field, the more mass it has. Photons, particles of light, don't interact with the Higgs field at all. That's why they have zero mass and always travel at the speed of light. Electrons interact weakly, so they're light. Top quarks interact extremely strongly, so they're almost 200,000 times heavier than an electron. The Higgs field literally decides the mass of every fundamental particle. But why does this field even exist? This is where things get beautiful and where the real physics genius comes in. Back in the 1960s, physicists had a huge problem. They had developed a stunningly successful theory called the electroweak theory that unified the electromagnetic force and the weak nuclear force. The math was perfect. It was gauge symmetric, which is physics speak for the equations look the same from every direction. But there was one fatal flaw. The math predicted that the force-carrying particles for the weak force, the W and Z bosons, should be massless, just like the photon. In real life, the W and Z bosons are heavy, really heavy. The W is about 80 times the mass of a proton. If they were massless, radioactive decay would be completely different and the universe would look nothing like it does. So the theory was mathematically elegant but physically wrong. Something had to break that perfect symmetry. Enter the Higgs mechanism. In 1964, Peter Higgs, Francois Englert, Robert Brout, and a few others independently realized the solution. They proposed that the universe isn't sitting at the symmetric top of the energy hill. It rolled down into one of the valleys. This is called spontaneous symmetry breaking. The laws of physics are still symmetric, but the ground state, the vacuum, isn't. And when that happens, the field acquires a non-zero value everywhere, and particles that interact with it suddenly get mass. The math is actually quite elegant. The Higgs field has a potential that looks like a Mexican hat. The symmetric point at the center is unstable. The universe chose one of the lower energy valleys. Once it's there, the field has a constant background value, and that background value is what gives mass. For the W and Z bosons, the mechanism is direct. The gauge symmetry gets broken. 3 of the 4 gauge bosons eat the would-be Goldstone bosons and become massive. The photon stays massless because the electromagnetic symmetry remains unbroken. That's why electricity and magnetism still work the way they do, while the weak force is short range. What about quarks and leptons, the matter particles? They get their mass through a slightly different route called Yukawa couplings. The math term is MEF, which finds fracka YF, VTR, SKRT2. where YF is the Yukawa coupling constant, how strongly the fermion talks to the Higgs, and Nuri VH is the vacuum expectation value of the Higgs field, about 246 GeV. The bigger, why ours? The bigger the mass. We don't know why the Yukawa constants are what they are. That's one of the big mysteries still left, but the mechanism works perfectly. So the Higgs field is the reason you have mass. I have mass. Planets have mass. Everything made of atoms has mass. Without it, electrons would be massless, and atoms couldn't form. Stars couldn't shine the way they do. The entire periodic table would collapse. Life as we know it simply wouldn't exist. Now let's talk about the actual discovery, because finding this thing was an absolute engineering and scientific miracle. The Higgs boson is not the field itself. It's the ripple, the excitation of the field. Think of the field as an ocean, and the boson as a wave on that ocean. To create one, you need to slam particles together hard enough to kick the field and produce that wave. The predicted mass was somewhere around 125 GeV, heavy enough that only the most powerful collider on Earth could reach it. That collider was the Large Hadron Collider at CERN. Two beams of protons, each with 7 TeV of energy, colliding 40 million times per second. Two giant detectors, Atlas and CMS, built like cathedrals underground, each weighing thousands of tons with millions of channels reading data every bunch crossing. For years they hunted. They looked for the characteristic decay signatures, 2 photons, 4 leptons, or B-quark pairs. The signal was tiny, 1 Higgs for every trillion proton collisions. Background noise was insane. Then, on July 4th, 2012, both Atlas and CMS announced they had reached 5 sigma significance, the gold standard for discovery in particle physics. Peter Higgs and Francois Englert were in the audience. You could see the emotion on their faces. The boson had been found almost exactly where theory predicted. Why was this discovery so monumental? Let me count the ways. First, it completed the standard model. Every single particle predicted by the model had now been found. For 48 years, the Higgs was the last missing piece. The puzzle was finally solved. Second, it proved that spontaneous symmetry breaking really happens in nature, a concept that also explains how the early universe went from a hot soup to the structured cosmos we see today. Third, it gave us the first direct look at a scalar field, a field with no spin. All other fundamental fields, electromagnetic, weak, strong, gravity, are vector or tensor fields. The Higgs is unique, and scalar fields are exactly what cosmologists think drove cosmic inflation right after the Big Bang. So the Higgs discovery gave us confidence that the same physics that works in our labs also worked in the first 10 or 32 seconds of the universe. Fourth, it ruled out a huge number of alternative theories. Many extensions of the standard model predicted multiple Higgs bosons or completely different mass generation mechanisms. The fact that we found exactly 1 Higgs at exactly the predicted mass was a massive constraint on new physics. The 2013 Nobel Prize in Physics went to Peter Higgs and Francois Englert. Robert Brout had sadly passed away. It was one of the fastest Nobels in history, only 1 year after discovery. That tells you how important it was. Let's zoom out for a second. Without the Higgs mechanism, right after the Big Bang, all particles would have stayed massless and traveled at light speed. There would be no time for atoms to form, no chemistry, no stars, no planets, no you. The Higgs field turning on was literally the moment the universe went from pure energy to having stuff. That's why some people legitimately call it the God particle. Not because it created the universe, but because it made the universe able to create everything else. Since 2012, we've measured the Higgs boson's properties with incredible precision. Its spin is 0, its parity is positive, its couplings to W, Z, top quark, bottom quark, tau, lepton, and even photons all match the standard model predictions almost perfectly. We've even started measuring its self-coupling, how 2 Higgs bosons interact with each other. But we're not done. The Higgs is still the most mysterious particle we have. Why does it have the exact mass it does? Why are the Yukawa couplings so wildly different? Electron versus top quark is 10^5 difference. Is the Higgs field responsible for dark energy or inflation? Could there be more Higgs bosons out there? These questions are exactly why the LHC is still running and why future colliders like the FCC or ILC are being planned. The Higgs boson didn't just answer a question, it opened an entirely new chapter in our understanding of reality. It showed us that empty space isn't empty. It showed us that the mass of everything around you comes from an invisible field that's been there since the first trillionth of a second after the Big Bang. And it proved that human curiosity and engineering can answer questions that once seemed almost religious in scale. So next time you pick up a coffee mug and feel its weight, remember, you're feeling the Higgs field at work. That's not philosophy. philosophy, that's physics. If you want more deep dives like this, symmetry breaking, quantum field theory, or what comes after the standard model, hit that like button, subscribe, and drop a comment. What's the next mystery you want me to explain? I read every single one. Thanks for watching, stay curious, and I'll see you in the next video. This is Physics Vault, where we don't just learn physics, we feel the universe.